Hello everyone, I am Himanshu Mishra and welcome to this last tutorial of this session. So this is week 12 tutorial. So today I'm going to discuss about the question related to the heat exchangers. So I'm trying to cover both concept like logarithmic mean temperature different concept and the NTU concept. And I will be solving a few questions related to heat transfer. Last week we wrapped the radiation heat transfer. And yeah, so we can start with the today's session. So let's solve the first question. So the first question is a cross flow air to water heat exchanger with an effectiveness of 0.65 is used to heat water, and we have given the specific heat of water and hot air. The water enters the heat exchanger at 20 degrees Celsius at a rate of 4 kg per second, while air enters at 100 degrees Celsius at rate of 9 kg per second. If the overall heat transfer coefficient based on the water side is 260 watt per meter square, determine the heat transfer surface area of the heat exchanger on the water side. Sorry. So assume the both fluids are unmixed. So we have given the cross flow heat exchanger, and the basic assumptions are steady operating conditions are there. And heat exchanger are well insulated. That means there is no heat transfer between inside of heat exchanger to the surroundings. And the third assumption is the overall heat transfer coefficient U is a constant and uniform. It doesn't change with time or space. So with this three assumption, let my heat capacity for hot and cold fluid are So this is my heat capacity for the hot fluid, which is my mass flow rate is 4 kg per second and my heat capacity is 4.18. So basically I'm considering here water. Which is 16.72 kilowatt by degree Celsius. My heat capacity of cold fluid will be this, which is 9 into 1.01. It's air and it's water. So this is for the heat capacity of cold fluid. Just a second. So from above, we can see that the heat capacity of air is minimum, which is 9.09. So my minimum heat capacity is coming from air. So my ratio of heat capacity will be C minimum by C max. So which is basically C of air and C of water. So it is around 0.544. Now since I have a cross flow air to water heat exchanger, to find the NTU here, we will be using the charts. So there are various kinds of charts that you can find in the textbook, which is basically for effectiveness versus NTU charts, and they have plotted for different value of heat capacity ratio. So these are for different value of heat capacity ratio. And in the question, we have already given this. We have already given the effectiveness, I think. So we already have now heat capacity here. And we already given effectiveness. So our effectiveness here is 0.65, which means that we already know effectiveness and we already calculate the heat capacity ratio. So for this specific heat capacity ratio, which is 0.544, and for effectiveness 0.65, let's say this is my 0.65, and for a specific value of 0.54, let's say this is my 0.544, I can calculate my NTU from plot. So for the cross flow heat exchanger, You can look out this plot in any textbook, this NTU versus epsilon plot. So let me just see again. We already given the effectiveness in the equation, which is 0.65, and we calculated the heat capacity ratio, which is 0.544. So this is my 0.65, and let's say this is my 0.44 heat capacity. So for this, I can get my NTU. So just try to look into the book. It will be very useful for the cross flow heat exchanger because you have to use the graph for calculating the NTU. So for effectiveness 0.65 and heat capacity ratio 0.544, from graph I will get NTU 1.5. So this is my NTU for cross flow heat exchanger. So I can now use NTU relation, which is my overall heat transfer coefficient, my surface area divided by my minimum heat capacity. So I can find my surface area as my NTU is 1.5, my minimum heat capacity is 9.09, and we have already given the overall heat transfer coefficient of water, which is 0.260 in kilowatt meter square degree Celsius. So my heat transfer area will be 52.4 meters square. So let me revise the things. So we have given the cross flow heat exchanger, we have given the properties of water, and we have also given this effectiveness of the heat exchanger. We have given the inlet temperature and the mass flow rate, and also the overall heat transfer coefficient, and we need to calculate the surface area of the heat exchanger. Just to be sure, we have given the cross flow air to water heat exchanger here. So first we calculate the heat capacity for both the fluids, and then we identify which is the minimum. Then we calculate the heat capacity ratio, so which is minimum by maximum. So once we get the heat capacity ratio C, and we have given effectiveness epsilon, from the plot for cross flow heat exchanger plot, we can able to find the NTU, because for such heat exchanger it is suitable to find the NTU from the plots. If the heat exchanger selects a parallel or counter flow, then we might have used the analytical or semi correlations to find the NTU. But for the cross flow, it is always suitable to use the plots, because we don't have a easy expression for the cross flow heat exchanger to calculate the NTU. So for this plot you required heat capacity ratio and effectiveness. So we found the heat capacity ratio, and it is effectiveness is already given. And from the plot, which you can find from any book, heat transfer book, you can get NTU. So once you get NTU, you just use the general formula for NTU to calculate the surface area. So let's move to the next question. Thin-walled double pipe parallel flow heat exchanger is used to heat a chemical whose specific heat is 1800 joule per kg degree Celsius with hot water. We have given the heat capacity of the hot water. The chemical enters at 20 degrees Celsius at a rate of 3 kilojoule per second. Sorry, 3 kg per second. And while the water enters at 110 degrees Celsius at a rate of 2 kg per second. Okay. The heat transfer surface area is 7 meters square, and the overall heat transfer coefficient is 1200 watt per meter square Celsius. So we need to determine the outlet temperature of the chemical and the water. So we have given some certain quantities. So we have given chemical heat capacity, specific heat capacity, which is 1800. And for water it is 4180. The mass flow rate of water is 3 kg per second, and mass flow rate of chemical is 2 kg per second. And we have given the surface area, which is 7 meters square. And overall heat transfer coefficient is 1200. Yeah, 1200 watt per meter square Celsius. So we can just list some basic assumptions again. So my flow is in a steady operating condition, which means that my flow inside the heat exchanger is not changing with time. And my heat exchanger is well insulated. So there will be no heat transfer from inside the heat exchanger to outside surroundings. And my overall heat transfer coefficient is steady and uniform. And the kinetic and potential energy of the fluid is negligible. I mean, change in the kinetic and potential energy of the fluid is negligible. So in that way, my heat capacity rate or the heat specific rate will be constant. So these are my basic assumptions. So let's find the heat capacity rate of both hot and cold fluid. So for the hot fluid, my heat capacity is the product of flow rate and the specific rate of a hot fluid. So which is for the chemical here. Sorry, water here. It is 8.36 kilowatt per degree Celsius. And heat capacity for the cold fluid, similar expression. So here I am consider the specific heat in terms of kilowatt, because I am writing the expression in kilowatt, therefore I am omitting the 10 to the power 3 here. So these are my both heat capacity rate, and out of this my minimum heat capacity rate is due to the cold fluid, which is 5.4. So my minimum is Cc, which is 5.4 kilowatt per degree Celsius. So my ratio of heat capacity rate will be minimum by maximum, which is 5.4 by 8.36. So on dividing, I will get 0.646. So my maximum heat transfer will be Q max C minimum TH in minus TC in, because we have a parallel flow heat exchanger, which means that at the entry, this is my temperature variation and this is my entry temperature, and the difference in the entry temperature is the maximum, which will give the maximum heat transfer here. So I'm just putting the values here. So my C minimum was 5.4 in kilowatt by degree Celsius, multiplied by my TH hot fluid inlet temperature is 110, and my cold fluid inlet temperature is 20 in degrees Celsius. So my maximum heat transfer will be 486 kilowatt. So now since we have given the area here, we have given the area is 7 meters square and overall heat transfer coefficient is 1200, I can calculate NTU directly from the information. So my NTU will be UA by C minimum. So my U is 1200 watt per meter square degree Celsius, and my area is given as 7 meters square, and my minimum heat capacity rate is 5.4. It is given in kilowatt per degree Celsius. So on calculating this, I will get my NTU 1.556. So I got my NTU and I got my maximum heat transfer. So now I will calculate effectiveness, because if I calculate the effectiveness, I can found the actual heat transfer, which is actual divided by Q maximum. So when I found this actual heat transfer, I can found the outlet temperature easily. So for outlet temperature, I need actual heat transfer, and to calculate the actual heat transfer, I need effectiveness. So this is unknown, this is unknown. So I will try to find the effectiveness from the parallel heat exchanger formula, because we have given the parallel heat exchanger. So my effectiveness for parallel effectiveness for parallel heat exchanger will be given by this relation. So this relation is for the effectiveness for parallel heat exchanger. This works only for the parallel heat exchanger. So we just need to plug the values. So we calculated NTU as 1.55 and my ratio of heat capacity raise was 0.646. So I just need to find the values. So it will be around 0.56. So this is my effectiveness. So I got my effectiveness. So I can find my actual heat transfer, because effectiveness can also be defined actual heat transfer divided by the maximum heat transfer. And this is for the general case, nothing related to parallel heat exchanger or the counter flow or the cross flow. So now we have got effectiveness and we got the maximum heat transfer. And this is the only unknown quantity, actual heat transfer. So my actual heat transfer will be effectiveness multiplied by maximum heat transfer. So my actual heat transfer will be 0.56 multiplied by my maximum heat transfer was 486 kilowatt. So my actual heat transfer will be 272.2 kilowatt. So this is my actual heat transfer. And now I got the actual heat transfer, then I can easily find the outlet temperature of cold fluid as well as hot fluid. So for cold fluid, this is my actual, my heat capacity of cold fluid and temperature difference of cold fluid at outlet and cold fluid at inlet. So I just from this expression I can write like this is the unknown quantity. Actual divided by heat capacity of cold fluid. So just plugging the values here. 20. This is my inlet temperature of cold fluid, and my actual heat transfer we just calculate 272.2. And my heat capacity for cold fluid was 5.4 kilowatt degree Celsius, and it is in kilowatts. So we need to calculate this, and when we calculate this, then my cold fluid outlet temperature will be 70.4 degree Celsius. Similarly, I can calculate for the hot fluid. So again, this is my actual heat transfer, heat capacity of hot fluid, temperature of hot fluid at outlet, temperature of hot fluid at inlet. So my temperature of hot fluid at outlet will be plus. So again, just putting the values here. So inlet temperature of hot fluid was 110. Sorry, it will be inlet here, outlet here. So it will be minus here. So my actual heat transfer was 272.2. My heat capacity was 8.36. So it will be 77.4 degrees Celsius. So this is the outlet temperature of hot fluid, which is 77.4. And this is my outlet temperature of cold fluid, which is 70.4. So let me summarize. We have given a parallel flow double pipe heat exchanger, and we have given a surface area 7 meters square, overall heat transfer coefficient, and the properties of hot fluid and cold fluid. And we have also given the mass flow rate, and we asked to calculate the outlet temperature of both hot and cold fluid. So in order to calculate the temperature of hot and cold fluid at outlet, so this is unknown, we need an actual heat transfer. But from the data given, we can calculate NTU, and from NTU, if we want actual heat transfer, we need to calculate maximum heat transfer. So the step we follow, so to get the actual heat transfer, so to get this, we need to know about this effectiveness, and we also need to calculate maximum heat transfer. So we can calculate this easily because all we need is inlet temperature to calculate this, and we are already given the inlet temperature of both fluid or parallel. But situation will be different if it is counter flow heat exchanger. So we have given the parallel flow. So the maximum heat transfer depend on the inlet temperature, inlet cold fluid temperature, and inlet hot fluid temperature. But if the heat exchanger is counter flow, then it will be not the same. So since it is a parallel heat exchanger and we have given the inlet temperatures of both cold and hot fluid, we can easily calculate Qmax. But again, this is unknown and this is unknown. So we need to calculate this effectiveness, and for effectiveness we need to calculate NTU, because if effectiveness depends on NTU and the heat capacity rate for parallel and counter flow heat exchangers. So we use the parallel flow heat exchanger effectiveness formula, which is this function of NTU and C, and here we need to calculate NTU also. So we need to calculate NTU as well, and to calculate NTU we need heat capacity. So there is a step-by-step procedure. So first calculate heat capacity ratio, then calculate NTU. So you first calculate heat capacity ratio, then you get the NTU, then you calculate the NTU. Once you get NTU, and you also get the heat capacity ratio, you can calculate effectiveness. Then you calculate effectiveness by using the formula for the parallel heat exchanger. You get effectiveness, then you separately calculate the maximum heat transfer because it depends only on the inlet temperature of cold and hot fluid. So now you get this, and you already got this. So now you calculate actual heat transfer, maximum, then you calculate actual heat transfer. Then on 6, you can calculate outlet temperature of both hot and cold fluid. So we calculate the heat capacity rate of both hot and cold fluid. Then we calculate the ratio. Then here we have done calculation of NTU, and here we calculate the maximum heat transfer. And after we get the maximum heat transfer and NTU, we can easily get the effectiveness for the parallel heat exchanger. So it depends only on NTU and heat capacity ratio. And this is the formula for only for parallel heat exchanger. Then once you get the effectiveness, you can use the general effectiveness formula to calculate the actual heat transfer. And once you got the actual heat transfer, you can use this relation for cold fluid and the same relation for the hot fluid to calculate the outlet temperature of hot fluid and cold fluid. So it's a step-by-step procedure to keep calculating various things. You just need to remember the various formulas or various method to calculate the NTU and the effectiveness, which vary from heat exchangers. So for parallel and counterflow, you can use such relation to calculate the effectiveness, but for the cross flow, you need to use chart. So in that case, you already need NTU and the heat capacity rate to calculate the effectiveness. Or if you have given the effectiveness, you can use that effectiveness and the heat capacity ratio to calculate NTU. So let's move to the next question then. So in this question, water enters a 2.5 centimeter internal diameter tube of a double pipe counterflow heat exchanger at a rate 3 kg per second. Water is heated by steam condensing at 120 degrees Celsius. And the heat of vaporization is given as 2203 kg per kilojoule per kg. If the overall heat transfer coefficient is 900, determine the length of tube in order to heat water to 80 degrees Celsius. So we have to use two methods, log mean temperature difference method and NTU method. So we have given the water here. So this is my water inlet temperature, which is 17 degrees Celsius, and it is coming out from here at 80 degrees Celsius. And the hot fluid is flowing here, which is coming out at 120 degrees Celsius. So my assumptions are the same. Steady operating condition, no variation of flow with time. And my heat exchanger is insulated. No heat transfer between heat exchanger and surrounding. And the change in kinetic and potential energy is negligible, so there is no change in the specific heat rate or the heat capacity rate of both fluid. Is negligible. So I'm referring the change is negligible. I'm not saying kinetic and potential is negligible. the change in the kinetic and potential energy is negligible. And my overall heat transfer coefficient is constant and steady, uniform. So we already have now some basic consumptions here. So first we use the log mean temperature difference method. So let T1. So here we have given the counter flow heat exchanger. So my T1 will be hot fluid inlet temperature minus cold fluid outlet temperature, which is 120 minus 80, 40 degrees Celsius. So this is my T1, and my del T2 is hot outer temperature, and my inlet temperature of cold fluid, which is, so my hot outlet temperature is also 120, 17 degrees Celsius. So in the equation we have given that there is a evaporation. So water is converted into a steam by condensation here. So during evaporation or condensation, the temperature remains constant because the fluid will release the latent heat, and during this process, the temperature remains constant because the evaporation condensation process take place at the constant temperature. So my heat for the hot fluid, my temperature will be 120 at inlet as well as at the outlet, but my water, my cold fluid temperature will be changing. So it is 17 degrees Celsius at inlet, and at outlet it is 80 degrees Celsius. But for the hot fluid, since it is condensing because of the cold fluid, this condensation should happen at a constant temperature. So at inlet and at outlet, my temperature is constant, which is 120 degrees Celsius. And that's why this temperature and this temperature was equal, 120 and 120. So my delta T2 is 103 degrees Celsius. So my logarithmic mean temperature difference is given by formula. So this is the formula for logarithmic mean temperature difference. We just need to put the values. So my delta T1 was 40 and delta T2 was 103. So on calculating, my log mean temperature difference is 66.6 degrees Celsius. So I can write my heat transfer equation either as mCp delta T, which we used in the convection heat transfer problems. So from the energy balance in the convection heat transfer problem, we wrote as, so here I am considering only cold fluid. You can also consider the hot fluid if the temperature is different at inlet and outlet. But since there is a condensation, so only option is to use the cold fluid. So cold fluid outlet temperature minus cold fluid inlet temperature. So this energy balance equation we have used in the convection problems, in the internal convection problems. We can also define heat transfer specifically for the heat exchanger as overall heat transfer coefficient A, and my multiply by my log mean temperature difference. So this relation is similar to the Newton's law of cooling. So instead of using H for the heat transfer coefficient, we are using the overall heat transfer coefficient U. On instead of using temperature difference, we are using the log mean temperature difference. So this is only for the heat exchanger, specific only for heat exchanger. So even in the internal convection problem, we use two kinds of heat transfer process. One was using this energy balance and one was using the Newton's law of cooling. So to calculate the area here, this is unknown. We will balance this and this equation. So first calculate the heat transfer due to energy balance. So just putting out the values. I'm writing this in kilojoule per kg degree Celsius. My temperature difference is 80 minus 17. So 80 is my cold fluid outlet temperature and 70 is my cold fluid inlet temperature. So my heat transfer will be 790.02 kilowatt. So I can now balance with this equation here. U multiply A multiply log mean temperature difference. So we know this, and we know this, which is 790.02 kilowatt. So my area will be this. So 790.02 kilowatt divided by my heat transfer coefficient, which is 900 watt meter square Celsius. So I'm also writing this in kilowatt, which was 0.9 kilowatt per meter square degree Celsius, and my log mean temperature difference was 66.6. So my area will be 13.18 meter square. Now in order to calculate the tube length, we will be using area pi dl. So my length will be area by pi by d. So which is 167.8 meter. So this is the length of the tube we calculated by using the log mean temperature difference method, this method. Now we have to calculate the same thing, the length or the area, by using the NTU method. So we calculate first at by log mean temperature difference. Now we are calculating by NTU method. So here we don't need to calculate this quantity because this is only applicable to LMTD method. For NTU, we need to calculate the NTU and effectiveness and all to calculate the heat transfer rate. So we calculate the heat transfer using the energy balance. The temperature difference is cold fluid inlet outlet and cold fluid inlet. So we already calculated this here, which is 790.02. But for the counter flow, we can also calculate the maximum heat transfer. because we have given all the inlet and outlet temperature. So for the parallel flow, it was the inlet temperature for both hot and cold fluid. But for counter flow heat exchanger, the maximum will be hot inlet minus cold inlet. So basically, we can also write here hot outlet because the temperature is constant for hot fluid. So my minimum heat capacity was, so we have to calculate the minimum heat capacity here also here, which is so now since there is a evaporation or the condensation in one fluid, the other fluid will automatically have a minimum heat capacity rate. So we just need to calculate the heat capacity rate for the water. So my maximum heat transfer will be 12.54, which is this, divided multiply by inlet hot, which is 120. Outlet hot is also 120, and the inlet cold, which is 17. So my maximum heat transfer is 12916 kilowatt. So now we have actual heat transfer and we have a maximum heat transfer. So we calculate the effectiveness, because in order to use the NTU method, we need effectiveness or NTU. So my effectiveness will be 790 divided by 1291. So this is my actual heat transfer. This is my maximum heat transfer. So my effectiveness will be 0.61. Now, if there is a condensation or the evaporation in any of the heat exchanger, like let's say in the counter heat exchanger, then my NTU formula for such specific case will be minus log. So this valid only for the condensation counter flow heat exchanger. So we just need to put the values here, and my NTU will be 0.942, which means that now I can use my general formula for NTU to calculate the area. NTU C minimum by U. Just need to plug values. C minimum was 12.54. My overall heat transfer coefficient was 0.9 in kilowatt meter square Celsius. So my area will be now 13.12 meter square by NTU method. So this is by NTU method, and this area was by LMTD method, means log mean temperature difference method. So by log mean temperature difference method, I got area 13.18. By NTU method, I got area 13.12. So my length will be area by pi d. So my length will be here 167 meters. So my length 167 meter by NTU, and by LMTD it is 167.8 meter. It is quite accurate. By using both methods, we get almost the similar results. So let me just recap the question. So we have given the water, we have given the properties of hot and cold fluid, and we have given it is a counter flow heat exchanger, and there is a condensation also. So this data can be useful for the NTU method, because if there is a condensation, we need to use a specific NTU formula to calculate the NTU. And we have given the counter flow heat exchanger, which means it is suitable for log mean temperature difference method, because we need to calculate the log mean temperature difference itself. So we need to calculate the length of tube by using LMTD, log mean temperature difference method, and the NTU method. So first we use the log mean temperature difference. We calculate T1, del T1 and del T2, then log mean temperature difference here. Then we calculate the actual heat transfer. So here we use the properties and temperature of cold fluid. You can also use for the hot fluid if there is a temperature changing for the hot fluid. But since here the hot fluid temperature is constant due to condensation, we use the cold fluid properties and temperature. Then once we get the heat transfer, we use the heat exchanger heat transfer, LMTD heat transfer to calculate the area. We just use the energy balance here. So this heat transfer is this due to MCP delta T, and this LMTD heat transfer due to this. So by balancing the heat transfer rate, I calculate the area. Once I got the area, I can easily calculate the length. This is by LMTD method or the log mean temperature difference method. For the NTU method, again we will calculate the actual heat transfer which we already calculated in the LMTD. Then we calculate the maximum heat transfer, which is specific for parallel heat exchanger and counterflow heat exchanger, depending upon the which temperature you are considering. Uh, Luckily, we have a constant hot fluid temperature, so we just consider that, and we have a maximum heat transfer. We already have actual, so we calculate the effectiveness from that. Once we get the effectiveness here, we use the NTU relation, which is valid only for the condensation. So once you got NTU, you can use the general formula for the NTU to calculate the area and then length. So basically, for the parallel flow heat exchanger, for the counterflow heat exchanger, for evaporation, and for condensation. For these four cases, you can use the formula to calculate NTU or the effectiveness, like such formula. And in the previous question, we also use this formula to calculate effectiveness. Otherwise, you need to use graph. So in the first question, we use graph to calculate NTU or effectiveness. So let's move to the next question. So this is a true or false question. So the first statement says that the value of effectiveness ranges from 0 to 1. It increases rapidly with NTU, but rather slowly for the large values. Therefore, the use of heat exchanger with a large NTU and thus a large size cannot be justified economically. So, since a large increase in NTU in this case corresponds to the small increase in effectiveness. So this statement is actually true, which means that first there will be a sharp increment in the NTU, but after that the increment is not much. So therefore we should use the NTU method till wherever we are getting the large increment in the NTU, but after that the method becomes less accurate. So the first statement is correct. So the second statement is for the NTU and heat capacity ratio, the counterflow heat exchanger is highest effectiveness, followed closely by cross-flow heat exchanger when both fluid are unmixed. The lowest effectiveness for the parallel flow, which is again correct. So the highest effectiveness is you can get for the counterflow, then for the cross-flow heat exchanger, and the lowest is for the parallel flow heat exchanger. So this is the effectiveness if you have a different kinds of heat exchangers. So both statements are correct here, which means it's a true statement. So let's move to the next question. So a double pipe heat exchanger is constructed of a stainless steel. We have given the thermal conductivity of it. And the inner tube of inner diameter of 1.5 centimeter and the outer diameter 1.9 centimeter. And outer shell of inner diameter 3.2 centimeter depicted in the schematic below. The convective heat transfer coefficient we have given as 800 on the inner surface, and outer surface is 1200 for the fouling factor, and the two on the tube side. And we have also given fouling factor for the shells side. We need to determine the thermal resistance of a heat exchanger per unit length. So we have given the conductivity and the heat transfer coefficient at inside and outside, and also the fouling factor, and we just need to calculate the resistance. So my overall resistance will be given as my inner due to thermal convection heat transfer coefficient, then due to my fouling at tube side, then due to the heat conduction from inside wall to outside wall. Since my walls are cylindrical, so this resistance for the cylindrical geometry, which we have done in our initial weeks. And then the fouling factor at the shells side. And then my heat transfer coefficient at the outside. So basically we have given a pipe. So this is my pipe. So this is my first resistance. Then there is a fouling factor which is coming due to the impurities. So here there is a inside fouling factor, and here it is the outside fouling factor. So the resistance coming from HI first, inside heat transfer convection due to fluid. Then my inside fouling factor, which is this. Then my conduction within the pipe, which is this. Then my outside fouling factor, which is this. Then my outside heat transfer coefficient, the convection heat transfer due to the outside fluid and the tube, which is this. So we just need to put the values here. So my area is pi d L. This is my inside heat transfer coefficient, and this is my inside area using pi d L. My resistance of fouling factor given is and my outside diameter is this. This is my inside diameter. This is my thermal conductivity. This is my length. My outside fouling factor is this. So my outside area using pi d L. This is my outside heat transfer coefficient. So this is my resistance. So we need to calculate the whole resistance. So on calculating, we will get 0.053 Kelvin per watt. So This is my overall resistance which we got from this. So just to recap, we have given the heat transfer coefficient at inlet and at outlet, and the thermal conductivity within the wall, and the Fouling factor at inlet and outlet. So we need to find the total resistance. So for that, we first consider the resistance due to internal heat convection from fluid to the wall, which is this. Then due to Fouling factor, internal Fouling factor, which is this. Then within the tube there will be a heat transfer from heat conduction. So this is this. Then outside Fouling factor, which is this. And outside heat transfer convection from surrounding fluid to the pipe, which is this. So then we just put the values to calculate the total resistance. So let's move to the next question here. So in this question, we have given a hot exhaust gas which enter a fin tube cross through heat exchanger. At 300 degrees Celsius and leave at 100 degrees Celsius are used to heat pressurized water at a flow rate of 1 kg per second from 35 to 125 degrees Celsius. The exhaust gas specific heat is approximately 1000 joule per kg per Kelvin, and the overall heat transfer is given 100. Determine the area using the NTU method. So we have given the all inlet and outlet temperature of the both fluid. So we can easily calculate the maximum heat transfer as well as the actual heat transfer. Once we have an actual and maximum heat transfer, we can now calculate the effectiveness. Once we get the effectiveness, and we already have a heat capacity, from the graph we can calculate NTU that we have done in the first question. So my specific heat capacity for the cold fluid is and for the hot fluid so my hot fluid is mass flow rate of hot fluid is not given, so it is unknown, and it is also unknown. So to calculate the mass flow rate, we can use the energy balance. That means my Q will be So this is my heat transfer. If I consider the cold fluid, I can also write my heat transfer as if I consider the hot fluid. So this is my heat transfer, which this is with cold fluid, and this is my heat transfer with hot fluid. Both are same, which therefore I can write like this. Equal because both these heat transfers are same. This equals this. So just make this both equation equal. So I have given this. I have given all the temperature. Only I have to form this. So my mass flow rate for the hot fluid will be then from this relation will be given as this. Since both cold and hot fluid are water, this will be cancelled because the heat capacity is constant for the water at both temperature as of now. So this is my mass flow rate. So my mass flow rate will be, so my heat capacity of the hot flow rate will be mass flow rate in the specific heat capacity. This is my heat capacity of hot fluid, which is my outlet cold, inlet cold, my inlet hot, and my outlet hot. So my heat capacity of hot fluid will be 1889 watt per Kelvin. And for the cold fluid, it was 4197. You calculate the heat capacity for the cold fluid, which is 4197. So among this, the minimum is this heat capacity. So my heat capacity ratio is minimum by maximum, which is 1889 or 197, which is 0.45. So this is my heat capacity ratio. And the effectiveness, for effectiveness, we have to calculate the maximum heat transfer. So my maximum heat transfer is minimum hot inlet and cold inlet. So my C minimum is 1889. Hot inlet is 300 and cold inlet is 35. And then Q max will be 10 to the power 5 watt. Now to calculate the actual heat transfer, we can use either this relation or this relation, any of this relation, we will get the same. So I'm using this one for cold. So my actual heat transfer is 3.78 10 to the power 5 watt. This is my actual and this is my maximum. So I can calculate effectiveness. By maximum. So my effectiveness is 0.75. So since again it is a cross flow heat exchanger, like we have done in our first question, we use the graph NTU versus effectiveness. This is for different value of heat capacity ratio. So we know effectiveness, which is 0.75, and we know the heat capacity ratio 0.45. So let's say this is my 0.75 effectiveness, and let's say this is my 0.45 heat capacity ratio. So I can calculate my NTU from the graph. In the first question, we have done the same thing for the cross flow heat exchanger. So from graph, my NTU will be 2.1, let's say. Then I can use the NTU formula to calculate the area. My minimum heat capacity is this 1889, and my overall heat transfer coefficient is 100. So on calculating this, my area will be 39.7 meters square. So this is the question which is similar to the first question. So again, let me revise. So we have given a cross flow heat exchanger. We have given all the temperatures of inlet and outlet of both fluids. So we have first calculate the heat capacity ratio of a cold, but for the hot fluid we have not given the mass flow rate here. So we balance this energy, this heat transfer with this heat transfer. Both heat transfer are same here to calculate the this mass flow rate. So by balancing the heat transfer, we calculate mass flow rate, which is this for the hot fluid. Once we get the mass flow rate for the hot fluid, we calculate the heat capacity for the hot fluid. Then we compare the heat capacity of cold and hot fluid, and we found that for hot it is minimum. So the minimum heat capacity is for the hot fluid, which is 1889. Then we calculate the ratio of the heat capacity, which is 0.5. Now since we have given the all inlet and outlet temperature of hot and cold fluid, we can easily calculate the actual heat transfer as well as the maximum. So for actual, we use this relation. We use this relation for calculating the actual. You can use either one or any of them. You can use either cold or you can use for hot. You will get the same actual heat transfer. For maximum, we use this one where we define the inlet temperature of both hot and cold fluid. Once we get the maximum and actual heat transfer, we can use the effectiveness formula. And for the cross flow, we use the graph based on our effectiveness and heat capacity rate. So we calculate NTU. If we have given the parallel or counter flow, we can use their correlation, suitable correlation for them to calculate the effectiveness and the NTU. But for the cross flow, it is always suitable to use graph. Then once we get NTU, we use the NTU general formula to calculate area. So it's same as question 1. So let's move to the next question. So we have given a counterflow concentric tube heat exchanger which is used to cool a lubricating oil. The flow rate of cooling water is zero point 0.2 and the flow rate of oil is zero point 0.1. Oil and water enters at a temperature 130 degrees respectively. How long must be the tube? The outlet temperature of the oil is 60 degrees Celsius. So we have given the outlet of oil 60, inlet of water which is 30, inlet of oil which is 100. So in this question, let me use the LMTD approach because we have already solved couple of problems using NTO. So let's find the outlet cool temperature or outlet water temperature. So we have not given outlet water temperature here. So in order to find the temperature, we need to find the heat transfer. So this is my actual heat transfer where I consider the inlet and outlet of hot fluid, which is oil. So mass flow rate of oil is 0.1, and this is the specific heat capacity of oil. The inlet is 100 and outlet is 60. My actual heat transfer is 8524 watt. Now, as I said in the previous question, then we could have also used the cold fluid temperature difference and the cold fluid heat capacity rate to calculate the actual heat transfer. So we use this formula to calculate the actual heat transfer, but we can also use this. So now I already got my this from the above heat transfer. We can equate these two to calculate this outlet cool temperature. So my outlet cool temperature is this. We already know this, which is 8524 watt. And my inlet cool temperature is 30 degrees Celsius. My mass flow is 0.2 and my heat capacity is 4178 for water. So my outlet temperature is for cold water is 40.2 degrees Celsius. So now we got all the temperatures. Outlet cold 42, 40.2, inlet cold 30, and these are my hot, cold, and inlet temperature. So let me calculate the log mean temperature difference. So this is I'm writing for the counter flow heat exchanger. So this is my log mean temperature difference formula. So I can just put values. So on calculating, I get this 43.2. So actually we need to calculate the area or the length, and we can calculate area or length by using this in LMTD approach. So this is unknown. So we already know this. We already know this, but we don't know this overall heat transfer coefficient. So the overall heat transfer coefficient given by 1 by H naught and 1 by Hi. So this is my heat transfer coefficient at outlet of the tube, and this is my heat transfer coefficient at inlet of the tube. So to calculate the heat transfer, so this is also unknown. We don't know this. We don't know this. So we don't know U. We don't know A. A is finally to be solved. So to calculate the inlet temperature, let me use the concept from the convection heat transfer problem, where we use the Nusselt number correlation to calculate the inlet heat transfer coefficient. So to calculate the inlet heat transfer coefficient, we will use the Nusselt number correlation. But we also know that to use the Nusselt number correlation, we need to check whether the flow is in laminar or turbulent. So based on that, we can use the Nusselt number correlation. So to check whether the flow is laminar or turbulent, we know we need to calculate the Reynolds number. So I'm writing the Reynolds number in terms of mass flow rate here. And this is my viscosity of water. So my Reynolds number is 14,050, which means my flow is turbulent. So for turbulent flow, we know how to calculate the Nusselt number by using correlation. And my Nusselt number is, we just need to plug values. My Prandtl number of water is 4.85. So my Nusselt number is 90. Sorry. Then I can use my Nusselt number correlation generally. Okay, so my inlet heat transfer coefficient. So my inlet heat transfer coefficient is DI. My heat conductivity is 0.625 and my inlet diameter is 0.25. So my inlet heat transfer coefficient is 2250 watt per meter square Kelvin. So again, to just recap, so to calculate area, we need to use this relation. So my area is unknown, and my overall heat transfer coefficient is also unknown. We have only known this log mean temperature difference, and we calculated actual heat transfer. We also calculated log mean temperature difference, but both these quantities are unknown. So to calculate the overall heat transfer coefficient, I have this relation where I have given the resistance of outlet heat transfer coefficient and the inlet heat transfer coefficient. Again, these two are unknown quantities. So to calculate the heat transfer coefficient at inside, we use the concept from the convective heat transfer, where we use the Nusselt number correlation. So to find which Nusselt number correlation to use, it depends on whether the flow is in laminar or turbulence. So to calculate, also to know whether the flow is in laminar or turbulence, we need to calculate the Reynolds number. So from the Reynolds number, we come to know that the flow is turbulent. So we are using the turbulent Nusselt number correlation. Once we get the Nusselt number, we use the general formula for the Nusselt number to calculate the heat transfer coefficient. So this is my inlet heat transfer coefficient. Now to calculate the outer heat transfer coefficient, I will use a similar concept, similar procedure. I will calculate the Reynolds number at outlet. So since it's an annular flow, I'm using D naught minus DI. So my Reynolds number at outlet is 56, which is at outlet it is laminar. So my Nusselt number will be at outlet is using the Nusselt number correlation here for the laminar flow. So this is for turbulent flow. For the laminar flow, I guess I don't remember correctly, but it is this. So my Nusselt number by from calculating this, which is only valid for laminar flow, will be 5.63. So my heat transfer coefficient at outlet will be so again putting the values 38.8 watt per meter square Kelvin. So again here I'm using the similar concept. I use the Nusselt number correlation and finding the heat transfer coefficient here. So for the first inlet case, for inlet heat transfer coefficient, the flow is turbulent, so we use the Nusselt number for turbulent. For the outlet case, for this outlet heat transfer coefficient, the Nusselt number was, Reynolds number was laminar. It shows the laminar flow. So I use the Nusselt number correlation for the laminar flows and calculate the outer heat transfer coefficient. So I know outer heat transfer and inlet heat transfer coefficient. Now I can calculate U. So outer is 38.8 and inlet is 2250. So on calculating, my U will be 38.1 watt per meter square Kelvin. So now I got U. I can now use this relation. So I got this, and I got this. I need to calculate A. So the actual heat transfer we found at the early was 8524. This U we get as 38.1 this. And the log mean temperature difference was 43.2. And I can write this as pi dl. So my L will be 8524 pi, and my di is inlet diameter is 0.025. So my length will be 65.9 meter. So just to recap, we have given the inlet temperatures of hot fluid and we have given the properties. So first we calculate the LMTD. We calculate first actual heat transfer. Then we calculate the outlet temperature of cold fluid. Once we get the all temperatures, we calculate the LMTD, and then we use this relation to calculate the area. But U was unknown, A was unknown, and we only calculate the actual heat transfer and the LMTD. So to calculate U, we use this relation. But again, my inlet and outlet heat transfer coefficient, HI and H0, unknown. So we use the convective heat transfer concept, where we calculate the Nusselt number based on the laminar or turbulent flow to calculate the heat transfer coefficient. So based on, we first calculate the Reynolds number to identify the nature of flow. So the inlet case, it was turbulent. So we calculate the Nusselt number for turbulent case, and then heat transfer coefficient at inlet. For the outlet case, the flow was laminar. So we use the Nusselt number for the laminar case to calculate the heat transfer coefficient at outlet. Once we get HI and H naught, we calculate U, then we calculate area and length. So that's it for the today class. So today we have solved some couple of problems related to the heat exchanger. So we use both NTU method and LMTD method to uh, find the area, heat transfer and temperature at the outlet or inlet. So we have looked some basic step-by-step procedure to how to keep calculating the effectiveness NTU and thereby the temperature or the area, whatever is the unknown in the question. So these are the same procedure you need to follow for almost every question using the LMTD and NTU approach. So you can use any of the approach if you are given the temperature of all hot fluid and cold fluid at all inlets. It's not like that NTU has some certain restriction uh, and LMTD has some certain. So you can use both. So especially if you have given the parallel and the counter flow heat exchanger, you can easily use the NTU correlations. You can use the formula for NTU, but for the cross flow, you have to use the graph. So for the cross flow, either you can use graph if you are approaching by NTU method, or you can just use the LMTD approach, because LMTD approach has only depends only on the temperature difference at inlet and outlet, and you have to use the log mean temperature formula for that. So yeah, that's it for today. So you can check this video on YouTube. You can also revise the previous concepts of convection and conduction heat transfer on YouTube. I will upload this PDF on the Google Drive, and you can access the Google Drive also. So thank you.